In this video, we're going to do a runtime analysis of selection sort. So by the end of this video, you should be able to do this kind of analysis on your own. Let's just get started by remembering what selection sort does. So the idea behind selection sort is to find essentially the smallest value in the remaining unsorted array and put that at the start. And then just keep repeating that process over and over. It might be easier with an example. What we have here is an array that's unsorted. The first step is going to be find the smallest value in this array. So you're going to walk all the way through, you're going to look at 4, 7, 2, 10, 1, and 8 and figure out that 1's the smallest. And you'll put 1 at the start. You actually swap 1 and 4 in the process. So now you essentially have your sorted array on the left, and you have your unsorted array on the right. You're going to do the same process again now for the unsorted array on the right. You're going to try to find the smallest value. You're going to look through all the elements, 7, 2, 10, 4, and 8, and find that 2 is the smallest, and swap that with 7 to put that at the start. Let's do one more example of this. So we look at the unsorted array again. We're going to find the smallest value. This time the smallest value is going to be 4. We're going to swap 4 and 7 and put 4 at the front, to put 4 at the front. At this point, we just continue this process, and essentially we end up with a sorted array. So that's the idea behind selection sort, but now let's talk about the analysis. Here's the code to essentially do selection sort. We have our method name is selection sort. It takes in an array of double or ints, which are just the values that we're trying to sort. In terms of analysis, we can kind of start walking through these steps. The first is just the initial values that you're declaring. You don't need to worry about this variable assignment. This is a constant time operation. But then we immediately get into a loop. And when we get to loops, we know that we're going to want to do a more careful analysis. In fact, this is a nested loop, and we'll talk about those details in a moment. In fact, the idea here is going to be very similar to the previous ones that we've done, and we're going to try to reason about how many times the outer loop runs and how many times the inner loop runs. But this isn't going to quite work out for us, and we'll see how that turns out here shortly. So let's keep with this approach, though. So let's try to figure out how many times the outer loop runs. The outer loop is actually pretty easy to reason about. It's going to run n times. So now looking at more detail in the inner loop, what we see is it starts off with index min equals I. This is just a single statement, so this is a constant time operation. At the very end of the inner loop, we're going to do a swap operation. And though it looks like I'm just calling it a nice function here, we have to think about what are the actual statements within that method. To do swap, it only takes actually 3 statements. So this again is essentially a constant time operation. Now we can dive into the details of the inner loop. So the inner loop is going to do essentially this testing for the keeping a running count of the minimum values that it's seen. So as it's going through, it's keeping track of, again, the smallest value that's seen, and in doing so, it's doing a conditional operation and then setting that value. A conditional, along with a value setting, is again just 2 statements. So we can consider this a constant time operation. So now that we have this constant time operation here, we have to start reasoning about how many times does this loop execute. Well, it's going to execute essentially n minus I plus 1. And where did I get that from? N is essentially the length of the array, and if you notice, j always starts at I plus 1. So it's going to keep increasing as we go through, as I increases. This is going to cause problems for me in a little bit, but we'll get back to that in just a second. So let's assume that our inner loop essentially fills in this runtime. We know that those first and the last operations are constant time. I can combine all of this into now one larger statement. I know those constant time operations can essentially be dropped, and I'm left with just a fairly clean term, which is just O of n minus I. What I'd like to do then is do the same kind of analysis we've done in the past, which is take the number of iterations that execute in the outer loop and multiply it by the number of iterations on the inner loop. And if I do that, I essentially get this nice form. The problem here is, what is O of n minus I? That's not what we want. We want this to be in terms of n. And I is going to be changing on me, so this is really problematic. I need to know specifically what does this mean in terms of n. Now the way I can do this is essentially look at the fact that as I increases, this term is going to decrease. But it's not enough just to say that, because if I increases rapidly and the term decreases rapidly, I make it a very different runtime analysis. The way I'm going to want to do this is to, instead of doing one loop at a time, let's look at them together. So what I'm going to do then is look at the entire operation of the outer loop along with the inner loop to figure out at each step how many iterations have to run of the inner loop. So when I is 0, how many iterations have to happen on the inner loop? Well, when I is 0, n minus 0 is n, and that just gives me n. Next iteration of the outer loop, I'm now going to have I be 1. N minus 1 is how many times that's going to execute. I is going to go to 2, we're going to have n minus 2, and this is going to go until we hit the end of the array. In that iteration of the loop, when I is the n minus 1, we're going to have just 1. So this sequence is what we're going to start reasoning about. How long does this take? How many steps is this? We have the entire performance within this series, but let's reverse it to work with it more easily. The way I want to reverse it is just swap the order. And now I'm seeing a series that might be more easy to work with. I see that it's 1 plus 2 plus 3, all the way up to plus n. And this might be a series you've recognized before, but let's talk a little bit more detail about how we might solve for this series. So what exactly is this? Well, there's a way to solve this. And I actually want to derive the equation for this because it's not that hard to do. And the way to derive this essentially is by looking at pairings. And what I want you to see is that this pairing, 1 and n minus 1, adds up to n. Likewise, 2 and n minus 2 also add up to n. And you can keep going this way through the entire list. So what I want you to do is just take a moment and think about how many total pairs add up to n within that range. All right, so if you came up with essentially the number of elements here is n minus 1. Each of them have to be paired up, so this should just be n minus 1 over 2 is the number of pairs that sum to n. That'd be exactly right. So how many operations are occurring here? Well, if each of these sums up to n, I can just say n times n minus 1 over 2. This is a pretty clean form. Now you might notice I'm missing one term here. I'm not adding on the n at the end, and I can just do that right here. Now this is a fairly recognizable series. And the reason why is because there's a fun fact about it. The legend goes that Gauss was assigned some busy work as a student, and in doing so, essentially derived this formula. And the busy work that he was assigned was to add all the numbers from 1 to 100. And when the teacher assigned this, she thought, okay, well, everyone's going to go 1 plus 2 plus 3 plus 4, and it's going to take them a while, and I can get a little bit of a break. The problem is Gauss derived this equation fairly quickly. He just plugs in the numbers, and out comes the answer of 5050. His work's done. He can move on. So this is a fun story. I always enjoy hearing about this, but this is where this equation comes from. All right, let's wrap this up by looking at the analysis. So we've got it down to this equation. What's the tightest correct classification then for this equation? Nice work. There's a lot of different ways that you may have solved this problem, but almost certainly what you did was you expanded out that first set to say n times n is n squared, and then you saw that the rest were all constants or just terms of n. Since n squared is the dominant term, this is going to be O of n squared, and we've essentially solved this problem. So working through selection sort wasn't incredibly straightforward from the start, but you can see if you do a careful analysis of it, we can come up with the solution.